Hello, and welcome to the second notes video for college statistics. All right, so the first note video, we kind of just got down some vocabulary. The second one's going to be focused on analyzing categorical data. So again, from last class, categorical data, things that you can put into different categories, sort of discrete values. Remember, categorical variables have values that are labels for the categories of which the individuals belong. So today is all about analyzing data. Because if you think about it, statistics is really about pulling information from large sets of data. All right. So let's just say that we were gathering data on whether somebody was left-handed or right-handed. And we talked to lots of people, and this person was left, left, right, 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 left, left, right, 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 left, right, left, right, right, left, 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 right, 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 left. All right. So that's data. All right. It's hard to gather any information when you're just looking at data. All right. This isn't even that much data. All right. You could have data on millions and millions of different things. This is what, like 15 or 20. I'm not going to count them out. But statistics allow us to take data, analyze it, and then glean some information from it. Be able to make an insight about the data that you can't do just by looking at the raw feed. All right. So what we're going to see is there's different tools and there's different methods that are appropriate based on the type of data that you have. And today we're going to be focusing on categorical data. So let's start with the distribution of categorical data. It is a list of the categories and their counts or percents. And then I'm just going to add often shown as a graph. So distribution of this little example out here would be the two categories are left and right. And then I would provide how many were left, how many were right. And even something as simple as that starts to provide information to the reader. All right. It gives them a basis of comparison that's much harder to do when you're just looking at raw data. So here's another example. Who buys Macs? So two different ways of showing it, but this is basically saying what was the previous computer that you owned? Did you not own a computer? Did you own a PC? Did you own a Mac? And then this is how many of each there were. All right, this is that same exact information, but instead of represented as counts, it's represented as a percent. So if we were looking at 500 people that bought Macs, 85 of them, it was their very first computer. 60 of them used to own a PC and now they're buying a Mac. And 355 of them used to own a Mac and now they're buying another Mac. Or we could put it in terms of percent. So 17% didn't own a computer prior to this. 12% did own a computer, but it was a PC. 71% owned a Mac. So what you can already see is you can start to gain information from this. Like, okay, a lot of people that buy Macs previously bought Macs, which tells you something about like loyalty to the brand, right? So even something as simple as this allows us to start getting insights that are hard to fathom when you're just looking at raw data. Just a point of emphasis here, when we use the counts, we call it a frequency table. And when we use the percents, we call it a relative frequency table. Okay. Round off error. This is just something that might pop up when you're making a relative frequency table. So this relates to the relative frequency tables. And it's just basically when you round multiple times, your percents might not always add up to exactly 100%. And that's fine. Like it's just an accepted part of doing these. And you don't have to like manually correct it. So, the definition we're going to put here is rounding multiple times can cause percents to something like 100.1% or 99.9%. This is not a mistake you need to fix. All right, so it's just an accepted result of rounding. If you're making one of these tables, you don't have to concern yourself with it not adding to exactly 100%. I mean, a very simple example would just, let's pretend you've got like somebody's favorite type of food. All right. And they list, it's a good type of food. We'll keep it easy. We'll say pizza. So creative, right? Burgers. It's weird that I'm putting burgers, given that I'm a vegetarian, but there we are. And we'll say salads. Okay. And then we might have a count. And just to keep it super easy, 1, 1, 1. If we were doing a percent, 1 out of 3 might be 33.3. 1 out of 3 would be 33.3. 1 out of 3 would be 33.3. If we were to add those all together, they would add up to 99.9. And we just don't worry about that. All right. We just accept it as it's going to happen sometimes. It's the nature of rounding. It's the nature of repeating decimals and so on and so forth. It's not always going to perfectly work out. That's okay. We just kind of proceed like it's no big deal. I totally didn't just drop my pen there. So yeah, that's all I really got to say about that. All right, flipping over to the back. Charts are great, but usually graphs are what you're going to see. You're reading an article, you're reading a newspaper. Graphs are a quicker way to express large amounts of information. So what are the charts that are most oftenly associated with categorical data? Pie charts, bar graphs. Those are the two that are going to get used more often than not. Segmented bar graph we'll talk about later. That's why it's in parentheses. Right now, we're just going to focus on pie chart, bar graph, two of the most common. And then let's just kind of talk about some of the differences here and why you might want to use one versus the other. Because remember, the whole point is conveying information. So depending on what information you want to convey alters what choice you should use when displaying that information. So a pie chart makes it difficult to compare categories, and I'm going to add visually. All right, because you can always put the numbers on it, and then the numbers make it easier to compare. But visually, it can be hard to compare categories. It can be hard to look at this wedge and this wedge and understand just how much bigger one is or the other. It can be hard to look at this wedge compared to this wedge and really understand just how much bigger are we talking about. All right. So it makes it very hard to compare categories visually. Again, you can always put the numbers on it and that helps. But if you're trying to give that like mental picture of what's happening, a pie chart is not the way to do that versus a bar graph. Much easier. It's much easier for somebody to mentally like take this bar and say like, all right, 1, 2, 3, like maybe it's like 4 bars or so, and visually kind of make that comparison. So that's one thing that sort of you want to keep in mind when choosing which tool to represent your categorical data. If you're hoping that the user is going to be able to compare categories, you're probably better off going with a bar graph than a pie chart. In contrast, the pie chart is much more useful when trying to compare a category to basically the whole, or I'm just going to put everything else. All right. It's easy for me to say, all right, here's PC, here's everything else. Here's none, here's everything else. Here's Mac, here's everything else. With a bar chart, it becomes a lot trickier to say, all right, here's this bar, everything else is, and then you're like, all right, well, this bar is this high. So let me put this bar, pretend that it's up here, and then I can sort of compare between this and that. It just becomes very difficult to do. So it's one of those things that depending on what comparisons you're talking about, depending on what comparisons you want the consumer of your charts to draw, decides what you should pick. You know, it's not just which one looks prettier. It's not which one has better colors. There should be a logic behind the graph that you're choosing and the information or story that you're trying to convey. Because that ultimately statistics are a story, all right? It's trying to tell people about the data. Is it a boring story? Sometimes, but sometimes it can be a pretty fascinating story. Now, this one, I don't know, this is just me being stupid. I don't really think whether it's easy to draw by hand should matter in which graph you pick, because all graphs are pretty much made via computers these days anyways. But I'll throw it out there. There it is. Much harder to draw this by hand. You need like a protractor, a compass. Like who even owns those things anymore? So much more difficult to draw by hand. This one, you need like a ruler, maybe a piece of graph paper, depending on how specific you want to get. But much easier. Things to keep in mind, there should always be some sort of key, or at the very least, label your sections, one or the other, to make sure that somebody can properly interpret the graph. Percentages are often excluded, but they don't have to be. All right, so we can put this percentages right on there, and then that makes it much easier to see. Sometimes you'll see percentages. Sometimes you'll see just raw counts. Either way, both are sort of valuable there. Bar graph, just a couple of things to know here. Make sure that you have spaces in between your bars. There should always be spaces in between your bars. When we talk about the histogram, they're going to be together, but with a bar graph, you're supposed to be representing each one as a separate category, a distinct category, which is why we put spaces between the bars. It's to represent that each category is unique. Label both axes. So like this right here, not a great graph because it hasn't been labeled. All right. I don't really know what is going on this left-hand side here. It goes from 0 to 70. Are those percentages? Are those a count? You should always be labeling your graphs. So I could put percents here, and I could put, previous computer down here so that I actually know what I'm dealing with. And again, all of this stuff should be relatively obvious. You've been told how to make graphs before, but it's important to kind of just be explicit about it so we don't take anything for granted. And then this one is probably the most important, and it says, do not abbreviate scale, aka starting from 10% instead of 0% is misleading. All right, and let me explain why that could be misleading, and I'm going to do it through an exaggerated example. All right, so let's pretend I have a bar chart here, and I have percents over here. And I'm not just going to start at 10%. I'm going to start at, let's just say, I'm going to make this right here 98%. I'm going to make this 98.5%. And I'm going to make this 99%. All right. And I'm not even going to worry about the categories down below. I'm just going to make 3 bars. All right. These bars could literally represent anything. Actually, we'll say these bars represent how many people like math, how many people like computer science, and how many people specifically like statistics. All right. Now, when you abbreviate the scale, if someone were to take a quick look at this graph, they would say to themselves, oh, wow, look at how much more popular this stats category is than any of the others. Now, if they took time to look at the percentages, they would say to themselves, oh, wow, like they're actually not that different. 98, 98.5, 99, they're effectively the same. But people don't always do that. Sometimes they just try to visually look at something and take a quick picture of it. And if they took a quick picture of this, they would think there's a dramatic difference between those 3 bars. In contrast, when you use the whole scale, I'm just going to do a very abbreviated one right here, those bars end up looking something more like this, where you can barely tell that one is a different size than the other. Now, a lot of times people like this graph better because it looks more dramatic, but it's actually very misleading. All right. From a statistical perspective, this is a much better graph, even though it might not be as exciting to look at, because it's a better representation of what's actually happening with your data. Now, the reason this is relevant is because sometimes computers, when you tell a computer in Excel or Google Sheets or whatever to make a graph, it will automatically make it like this because it does look more dynamic. It does look more interesting. You as the user, you as the statistician have to know enough to actually go in and force the scale to be something that's going to be more accurate and more reliable. All right. So again, we are going to use computers in this class, but sometimes you as the user have to have enough information to override and correct the computer when it does something improper like this, because this would actually be the more accurate representation. All right. So flipping over to the next sheet, what I was just talking about with those graphs is something called the area principle. All right. And the area principle states that the area occupied by part of a graph should correspond to the magnitude of the value it represents. All right, which is basically just a long-winded way of saying what we just talked about with those bar graphs there. the area that the bar is taking up should correspond to like the actual value of it. So when we go back to sort of our dramatic graph here, the area is not reflective of these actual values that it's representing. Versus this one, the area is much more reflective. If we look at this, the area makes you think that this is 5 times as big, when in fact the difference is pretty insignificant. Pictographs often violate the area principle and mislead readers. So again, people like to use these because they seem more interesting. Like, oh, instead of having like a regular bar, let's use a picture. It's going to catch their attention more. Yes, it may catch their attention more, but it's probably going to mislead. All right, because when you're using pictures, they're usually growing across 2 dimensions. And if they're growing across 2 dimensions, the area is not staying the different areas are not staying along the same scale that you'd want them to be. And it's easy to demonstrate this with just like a quick sketch. So imagine you have a 2x2 picture. All right, here's my 2x2 picture. All right. From our super advanced geometry knowledge, we know that the area of a 2x2 picture is 4. All right. Now, because pictures tend to grow across 2 dimensions, because otherwise they would look stretched and weird, if we were to double the size of our picture and make it 4x4, all right, so here's my new 4x4 picture. Again, applying my super advanced knowledge of geometry, I would calculate that area to be 16. So while my picture was only supposed to be twice as big, 2 to 4, the area increased by a factor of 4 because the picture is increasing across 2 dimensions. All right, it's not just increasing the height, it's also increasing the width, which then makes the area grow even faster. Versus a bar, all right, when we make a bar higher, all right, when we make a bar higher, we don't also make it wider, so we're not getting that same distortion of area. So again, pictograms look cool, but from a statistical perspective, and do they even look that cool? From a statistical perspective, they are actually kind of misleading because they distort the area and give a misleading representation. All right. In this little example here, yes, Macintosh was the biggest. Mac was the biggest. There's no question about that. But the pictogram makes it look even more pronounced than it truly was. All right. So generally, as a good statistician, and presumably you want to be a good statistician because you're in this course, this is a tool that we try to avoid to use because it often paints like a misleading picture. Instead, we stick with bar graphs and pie charts, maybe not as exciting, but they offer a more honest representation of what's going on. And then the one that we choose depends on the story that we're trying to tell. Again, if we're having users compare one category to another category, we want to use the bar graph. If we're having users compare one category to the rest or everything else, that's where the pie chart comes in. So you shouldn't just be picking them randomly. You should have a reason on why you're picking the one that you're picking. All right. So that wraps this up. I'm also sharing a slideshow of some bad graphs. Take some time, look through it, see what kind of mistakes are made. And these aren't like, oh, students making mistakes. These are like professional mistakes that are happening on like graphics that make it onto like TVs and papers and everything else. And it just kind of shows you the importance of sort of understanding proper procedure when making these types of things. All right. So have a great day, and I will see you when I see you. All right. Bye.